Right. This is going to be a short video because what I want us to focus on for the next class is not necessarily physics, but I want us to review vectors. So I'll be linking to some of the videos that I've done for a previous physics course because I think everyone probably could benefit from some review on vectors. But let me introduce kind of the 1D version of Coulomb's law because we can still move forward with some physics concepts as we review vectors. So we've talked about how charges can interact with one another. We've seen evidence that there are forces going on between two charged particles that don't even have to be touching one another. And so to quantify this was studied and eventually written down in our kind of modern version by Charles Coulomb, who studied the forces between charged particles, pointing out that this is a force that only arises when you have two objects that have some sort of net charge on one another. They can then interact with one another. So this relies on particles being charged. Or again, as we talked about in that previous video, right, what I mean, if there's some sort of net charge, it's a net overall positive charge, a net overall negative charge. And this force he wrote down, and we could have studied this and tried to quantify this ourselves, right? We could have taken two objects, and charged them by rubbing it with fur or silk. And we could have seen that the more rubbing we do, it seemed that that would increase the magnitude of the force. Then we could have also taken two objects, rubbed them exactly the same way, and looked at as we placed the objects farther away from one another, that the force seemed to decrease. So it seems like it depends on the amount of charge as well as the distance between the two objects. And so then we can come up with the magnitude for Coulomb's law of force, which depends on some constant of proportionality, and then it depends on the charge on object 1, the charge on object 2, as well as the distance between the two objects squared, and that appears in the denominator. So to give kind of a picture of this, if we have some object here that has some net charge Q1, some charge here that has some net charge Q2, and then there is some distance here that represents the distance between charge 1 and charge 2. There is a force that is exerted on both of those objects that are equal in magnitude and opposite in direction. Of course, Newton's third law has to be obeyed, such that they are attractive when there are opposite charges, one's negative, one's positive, and it is repulsive when they are like charges, both positive, both negative. This K is sometimes called Coulomb's constant. And it has a value of 8.99 times 10 to the 9. And then you can think of the units. You know the units of force, and Q has units of coulombs, and R has units of meters, and SI units. You can work out that this then better have a unit of Newton meter squared per coulomb squared. So that when you multiply it by two charges, that gets rid of the coulomb squared in the denominator. When you divide by a distance squared, that gets rid of the meter squared in the numerator. Overall, you're left with Newton as the unit. We will also see that this K can be written in terms of some other more physically motivated quantities. So sometimes K is written as 1 over 4 pi epsilon naught, where epsilon naught has many names, but we'll call it the permeativity constant. Permeativity constant. And it has, or sometimes it's, the permeativity of the vacuum, or you might hear it called like the electric dielectric constant or something like that. It has a value of 8.85 times 10 to the minus 12 Coulomb squared divided by Newton squared meter squared. And we'll come back a little bit later in the course in terms of what this epsilon is, but for now we can think of the Coulomb's force as some constant k multiplied by the product of the charges of the two objects divided by the distance squared between the two, knowing for now that it is a force that points towards the two charges when they have opposite charges. So if I have, say, Q1, which is less than 0, and here it might be Q2, which is greater than 0, so one's positive, one's negative, then I would expect a force on both of those objects that are equal in opposite direction towards one another. If they both have the same charge, sign, both positive, both negative, it is a repulsive force. The formula here that we're seeing probably looks very familiar, right? This looks very much like gravity. Which, remember, was F equals some constant G m1 m2 over r12 squared. The differences, of course, is this is depending on charges, not masses. And the gravitational force was always attractive. There's only one flavor of, I guess, mass. And it always results in an attractive force between two objects gravitationally, though with charges there are two flavors. And it can result in an attractive force or a repulsive force. So it's a little bit more complicated than gravity, but not by much, in my opinion. So given that the force can either be attractive, and like I've drawn above, where if they have opposite signs, it might be repulsive, attractive to one another, or if they both have the same sign, say they're both negative, we would expect that then the force is repulsive, equal and opposite in direction. In that case, in talking about the Coulomb force, it seems like we have to specify both how strong it is, maybe I call that a magnitude, and in what direction it's pointing. So that really does sound like a vector, which we are going to review in the other videos, and then quantify this better as a vector in the next kind of conceptual video that we do for lecture 4. The one thing I'll say before I do a few examples, and then that'll be it for this particular video, is that like other forces, also obeys a superposition principle. And all that means is if I have some charge capital Q that I want to study, maybe that's my system, that's my object, maybe there's a Q1 over here, there's a Q2 over here, Q3 here, Q4 here, and they might be positive or negative. Each of those forces exert a Coulomb force on capital Q. And maybe Q1 goes in this direction, maybe Q2 goes in this direction, Q4 maybe also goes kind of in that direction, maybe Q3 goes in that direction. And in all of these cases, we could say, what is the net force on Q? Well, we just sum them all up. So that the net Coulomb force, and I'll write this as a vector, on capital Q is just the sum of the Coulomb forces from each individual charge, right? The Q1, the Q2, the Q3, the Q4. Again, this being a summation, I'm summing over I, which just ends up just being kind of F1 plus F2 plus F3 plus F4 for this particular example. So not too bad, right? We've seen a lot of this before. We just now have the additional kind of, complication that we have to think in terms of if they're like charges, they repel. If they're opposite charges, they attract. And if we think 1D, that's actually, we can think of some interesting problems to test our conceptual knowledge on this already. So suppose I have kind of 3 charges, and they're all separated by equal distances. So this is some distance d, this is some distance d. This is an electron, this is a proton, and this is also a proton. And I might say the magnitude of the force between the center proton and the electron suppose I say that it is equal to F. Right, if we had some numbers, we could actually plug in some numbers, get a number for this F. Let's just give it a symbol, because I usually work with symbols until the absolute last possible minute. Magnitude of the force between the center proton and the electron is equal to F. What is the net force? And this, I will say, magnitude plus direction on each particle. In this case. So if I know the force between the electron and the proton is equal to the magnitude is F, and I can think of the directionality, they are opposite charges, so the electron is pulling that center proton towards the left. I could then ask, what about the two protons? And then what is then the net force from everything? And then we'll look at the other particles. So let's think about the center proton first. The electron and the proton, those are opposite charges. And we said that the force between them is equal to F. And since it's an opposite charge, I know that the force is being pulled in this direction. So maybe I'll draw it as a red arrow of that length and give it the symbol F. I can then ask what's going on with the proton and the other proton. They're the same distance away. And we have to remember that protons and electrons have the exact same magnitude of charge, just one is positive and one is negative. So in terms of the force formula, the force from the electron and the proton we expect to be kind of negative because it's to the left, K, the charge on the electron times the charge on the proton, all divided by the distance between them, which we said was d squared. And the negative sign then is telling us it's to the left. And then we called that F. Just write that we call that F. And then specify to the left. Its magnitude, K E squared over D squared, is F, and then it's pointing to the left. The force of proton-proton, well, the K is still the same. The charges on the protons are still the same. They're both E, and they're the same distance away as the proton and the electron from each other. So it looks like the magnitude of the force is exactly the same. But then we can ask, what direction does it point? Well, they're opposite charges, so they're going to want to repel. So what I would expect that force then is pointing also to the left. That might be a force proton-proton, and then here this was electron on proton, on center proton. So it looks like the net force is -2 times F to the left. That would be the net force on that center proton. What about, say, the force on the electron? Well, the electron, we can just take them one at a time. We have the electron, and then there's the center proton, separated distance d. They're opposite charges, so I expect them to be attracted to one another. So the electron is going to want to be pulled towards the proton. I expect the force to be pointing to the right. And it looks like the force, from proton on electron is going to be plus k e squared over d squared, which is what we just called F. So I'll say plus F, the plus really kind of meaning to the right. Now we have to think about the electron and that other proton, which now is 2d away. It's twice as far away. Now they're opposite charges. I also expect it to be to the right, but I cannot say that it's equal to F because the formula depends on the distance. They're farther away from one another. I expect the force to be weaker. And this isn't too bad because we said before that F was equal to kind of k e squared over d squared. So this kind of new force, when it's twice as far away, I expect to be still k. The charges haven't changed. It's an electron and a proton. But now they're separated by 2d squared away. And notice, again, I put the 2 and the d being squared because the distance has doubled in this case. Then I can simplify. Looks like k e squared. Then the bottom becomes 4d squared. This looks like it's on 1/4. Then there's k e squared over d squared. And if I look at that thing in parentheses, that looks like what we called F. So it looks like in this case, the magnitude of the force is just 1/4 F. There is a force pulling the electron to the right. It is weaker. How much weaker? It's 1/4 as strong. So then the net force looks like it's F pointing to the right plus 1/4 F pointing to the right. So it looks like the net force on the electron is 5/4 F to the right. I'll let you try the third one on your own. I'll give you the answer. For the proton that's on the far right, it is going to be acted on by the electron to its left and the proton to its left, and it should have a net force that has a magnitude of 3/4 times F and points to the right. So try that out on your own. Okay, we're going to stop this video here, but there are other videos to watch to help you start to review vectors. So we'll practice this 1D Coulomb stuff with some vector review next time.